Hello and welcome to Embedded Internals. This is ninth episode of our series Pointer Thinking series. In this episode, we are going to understand different pointer bugs. Until episode 8, we have seen that pointers are very powerful. But in this episode, we are going to discover why pointers are feared. One thing we need to understand that every pointer bug is the same bug. Pointer points to address. So any bug occur at the pointer means there is some address corruption, either wrong address or wrong memory access. So when we say at the hardware level, it is simply we have one pointer which is accessing some address and memory access. However, bugs occur when address is wrong. Wrong address means pointer bug. Now, we have different kinds of pointer bug, although all bugs means there are some problem at address, but the nature of the bugs are different. So this is our pointer safety pyramid, where valid pointer usually means we are safe to go. Null pointer means some null access has been violated, or we are trying to access the memory which is null. While pointer which is more dangerous than a null pointer, dangling pointer, which is further danger, use after free, further danger, and memory corruption means we are at uh, memory corruption, dangerous pointer bug. In this episode, we are going to understand what are null pointer, while pointer, dangling pointer, why these problems occur, and how we can avoid that problem. Okay, let's start from null pointer. So null pointer, let us take an example, integer pointer ptr, which is null. Null means it is not pointing to cut. Null means pointing to memory location having the address 0 by 0. So inside the memory, pointer representation will be pointer pointing to some null value. It means points nowhere. When we try to dereference this pointer, dereference means read some value, or even when we try to write some value at this address. So pointer p write value 10. It means we are writing to address 0, or we can say access violation. We cannot write to this location, and corresponding result will be segmentation fault. So null pointer basically is a null 0 into 00 memory address. It means it is not pointing anywhere. When we try to write at that address, or we try to read from anything from that address, means we are violating the memory rule, and the result will be segmentation fault. Null is not always dangerous. Null is used for safety purpose. Null is not dangerous. When we try to dereference the value there, then then the result will segmentation fault. Otherwise, null is not dangerous. We use null pointer for safety. Like for example, we have a pointer. We have declared a pointer ptr, and then at the next statement, it means that pointer is pointing to some unknown location. When we declare the pointer as int ptr equal to null, this is termed as some invalid state, but this declaration is much safer than above one. Invalid but safer. So we use null pointer while we are declaring, but when we try to dereference the pointer, that time we are violating the memory and segmentation fault occur. While pointer means pointer never initialized. For example, integer ptr. So in the memory representation, this ptr is now pointing to some random memory location. So this is some random location, or this is termed as invalid location. So where actually our pointer is pointing, we don't know. The location our pointer is pointing to random. When we try to write any value, then the possible outcome will become either, so result will be either crash, corruption, silent failure. And this is worst error, works today but may fail later. So while pointer is a pointer which has never been initialized. So nobody knows at what memory location it is pointing. It is pointing to some random memory location. It can be an invalid location or valid, we don't know actually. So when we try to dereference that pointer or when we try to write any value at that location, the result will be either corruption, crash, silent failure, or may work today but later it will fail. We can say that value memory address it is pointing to may be inherited from the old stack contents which are never initialized, not controlled. So CPU is seeing that this is a valid looking memory but it is actually not valid, so it may crash anytime, immediately or maybe sometime later. So how to prevent the while pointer? To prevent it, we should initialize our pointer by null value. Null means it is pointing to some invalid state, but it is safer way of initializing a pointer. Now the third topic is dangling pointer. Dangling pointer means pointer is referring to a memory that no longer belongs to it. So dangling pointer is actually ownership problem. Pointer is not the owner of that memory location. This is most common professional bug. Let us take an example. Integer pointer ptr. We have a local function where we have declared a variable int x is equal to 10 and in our pointer put the address of x. When this or the functions go out of scope, so block exists or function scope ends, means x value destroyed. So x got destroyed but address of x we have stored in our pointer, so variable got destroyed but pointer remains. So the memory representation for same will be before when x is in the scope, pointer is pointing to address of x and at this address our value 10 exists. Whereas after the function goes out of scope or function exists, at that case pointer is still pointing to address of x but the value destroyed. So address is valid but object gone. This is dangling pointer. When we lost the ownership of the memory which sometime belongs to us. So when we try to dereference the pointer, possible output we may get is the value 10, any value 500 dash or any random value because the address is valid. All values may be legal but this behavior is undefined behavior. So the actual result is undefined behavior. So dangling pointer results into undefined behavior. We have heap dangling pointer, very common, like we have allocated some memory into pointer ptr. So in the memory representation it is like ptr is pointing to some valid address which is pointing to in the memory allocated and if we have provided any value, so valid location and valid value. When we free the memory, free ptr, then when we try to dereference the pointer, now allocated memory has already been freed. If we try to release if we try to read from released memory, because memory is still pointing to a valid location but the object has been gone, address is valid but object has been gone, so pointer is memory has been released but pointer not clear. So when we try to dereference the pointer, the result will be crash or any undefined behavior. Use after free. This is in most expensive pointer bug category. For example, in integer pointer we have allocated some memory like malloc. After we have allocated memory, we free the memory. Free the pointer means memory has been released. And after releasing the memory, when we try to read or dereference this memory, means memory has been released but not cleared. This will result in corruption because now the pointer is pointing to unrelated object. In the heap category, we have double free. This is also another very common bug programmers make, double free. So freeing the memory twice. Like we have allocated a pointer and free pointer ptr and again free the same pointer. So at this time valid memory will be released. In the second free we don't know which memory will going to released. Allocator metadata get damaged and the result will be heap corruption. So modern allocator often detect this double free, whereas in the older system we are not able to detect it. So memory corruptions. Like for example, we have declared an array of 3. So the possible memory will look like and some valid values, some valid values. Okay. But bug occur when we try to read the value out of allocated memory zone. So when we try to read array of 10, this is not the valid allocated memory. Try to read or try to write at this location, like till we will do array of 1, 10, valid, array of 0, valid, array of 2, valid. But when we try to write at array of 10 location, memory location we are trying to access is outside array, out of bound. So the result will be data corruption or memory corruption. So when we try to access the value which is out of bound, the corruption will occur. Sometime what happen when when in the large production we have some error like this. Program will not immediately give the warning or show some corruption or something. Program will continues, but at some hours later or few days later, code get crash. So it will become very difficult to debug this kind of error when we have the large production code base. Similar to array corruption, we have stack corruption as well. Stack corruption mostly occur when we try to write larger values. For example, we have a function where we have a buffer and the buffer size is 8. And we are string copying some data into this buffer. Let's see, hello world. So buffer is only of 8 character long, but we are copying 10 or 11 data. So this will result in stack corruption. So inside memory, where the snapshot will saved as, so we have buffer, we have saved frame pointers, and we have return addresses which are saved in our memory. So when we try to copy the data hello world to the buffer, write exceeds buffer. Okay, because hello world is 11, size is 11, where buffer size is 8 only. So write exceeds buffer. Yes, and return address over return. So memory corruption. So program will crash at some point. So final result will be program crash. And the reason is write buffer exceeds. In the heap corruption, like we have this double free, or when we try to do use after free, allocator metadata damaged. In the buffer corruption, in the stack corruption, stack metadata got damaged. Buffer overflow. Buffer overflow usually because of ownership. We are trying to write at buffer location which don't belongs to us. For example, we have a character buffer size 4 bytes. So in the memory representation, it is represented as this. When we will try to write, it is similar to array out of bound problem. Buffer memory location 10th. So this location does not belongs to us, out of our ownership, and writing to that location which is out of our ownership may result in corruption. One very common and frequent bug is when we are trying to return local address. Return local address. As function goes out of scope, So the address goes out of scope, and when we try to return it, it results in corruption. So let us take an example. We have created a function which is returning integer pointer. And in this local function, we have a local variable x having the value 10, which is of integer data type. And we are returning the address of x from this function. Now what will happen when this function, when after the return statement, x got destroyed, because the scope of this variable is a function scope. So once the function will exist, x will destroyed. And when the x variable is destroyed, this address become invalid. And the result we will get is dangling pointer. So we should be very careful when we are returning any address from local function, as this will result into corruption. Now we have memory leak. Actually, memory leak is not a corruption, but still it is pointer related. Therefore, I am covering it into pointer bug. Memory leak happens when we allocate the memory but forget to free it. Like in this example, we have allocated 10 bytes of integer data type, and without freeing, we set the pointer as null. It means pointer got lost. We are not able to reach this memory, so this memory become untraceable, unreachable. Therefore, leak is created. When in the large production environment, even once this kind of problem occur, so memory will kept on growing, system will kept on slowing, because lots of memory got allocated but never freed. So system will start growing slowly, and at some point of time we will face the crash. So memory leak is a very common bug which should be avoided. Memory leak means allocated memory has not been freed. Now, what are the defensive programming? So we should always mark pointer as null after freeing the pointer. Before dereferencing any pointer, just check if the pointer is valid or not. When we initialize any pointer, mark it as null immediately, so that we are not working on any wild pointer. When we are accessing array or buffer, always check that the range is in the valid bound, and try to use the safer alternative of string copy and other similar library functions when we are dealing with strings. Mindset when we are working with on pointer bugs. So whenever you see the pointer, just ask few questions to yourself. Where did the pointer come from? If the address you are working on is valid or not? Who owns the memory? Was the memory freed? Is the data type correct, or is the access out within bound? So the core law here is that pointer, we know that points to some address. So if the address is within the ownership, what is the lifetime of that address, and valid access or not? So whenever any problem occur at any point of time, anything break means some bug has been occurred. So in this episode, we have checked that all pointers bugs are at the end address bug. When we say null pointer means null means it is pointing to nowhere. So null pointer, a pointer which is pointing to null memory location. So there is an access violation, and when we try to dereference or read or write at that address, we will face the segmentation fault. Wild pointer contains garbage, means pointer which has never been initialized. So it will result in corruption. Dangling pointer means we have lost the ownership. Pointer is referring to a memory that no longer belongs to it. Heap pointer, there are lots of different types of error in heap, like we have freed the memory has been released but pointer not cleared. Use after free, we are trying to access the address when we have already freed it. The result will be corruption. Double free, freeing the same memory twice. Buffer overflow, as in case of array out of bound or string out of bound. Stack corruption, when write exceeds buffer length. It means the return address got overwritten. So program will crash. Buffer overflow, it is also related to ownership. means it has corrupted the memory. We are trying to write at the memory which don't belongs to us. We should be very careful. We should not return any local address, because when we are trying to return the address from the local function, means the variable goes out of scope, means address invalid, and the result in corruption. Memory leak, when we have allocated the memory but forget to free it. So memory corruption, one thing in memory corruption is that memory corruption often appears later. So it is very difficult to debug these kind of corruption in large production environment. We have some defensive programming. We should always take care of all these things. And pointer debugging basically means validating the addresses. So that's all in this episode. In the next episode, we are going to debug these things using the debugging tools like GDB, backtrace, memory dumps, address sanitizers, watch points, valgrind, core files, or live memory inspections. This is more of theoretical, when the next episode is more of practical. So stay tuned for same. Thank you.